Good morning, everyone, or good evening, wherever you are. Thanks again for joining us. Today we have Dan Freeman from St. Louis University. Dan is going to speak on a positive Schauder basis for L2. Take it away, Dan.
Well, thank you very much for the invitation to speak, Bunyamin. This is, I think, by far the largest audience I've had for a talk. Exciting.
By the way, people, I'm sorry about that. So if you can mute your microphone, that'll be great. Except you, Dan.
Okay, yes.
Okay, go ahead. Okay.
So I'm going to be speaking on joint work with Alex Powell and Mitchell Taylor. So I'll start with the basic definition of Schauder basis. And so we say that a sequence of vectors in a Banach space is a Schauder basis if every vector has a unique representation in terms of a series. And we say that the Schauder basis is unconditional if this series converges in any order. And if you have a Schauder basis, the uniform boundedness principle gives you some constant C, and we're going to call a Schauder basis C basic if the projection onto any initial sum in the basis is bounded by C times the norm of the full sum. And then we call a unconditional Schauder basis CU unconditional if you put any plus or minus 1 in front of the coefficients, that doesn't increase the norm by more than a factor of this constant CU. And we're also going to talk some about Schauder frames. And so for a Schauder basis, we just have a sequence of vectors. For a Schauder frame, we need a sequence of vectors and functionals. So xj is our vectors, and fj is our functionals. And then we call this sequence of pairs a Schauder frame, or a quasi-basis, if this linear reconstruction formula holds for every x in the Banach space. And so a Schauder frame is a generalization of a Schauder basis, because if you have any Schauder basis, you can pick biorthogonal functionals, and then the pair of your Schauder basis with the biorthogonal functionals is a Schauder frame. So the main question that we will be considering in this talk is what kind of coordinate systems you can build for LP using only non-negative functions. So let's look at some nice examples of Schauder bases for LP. So we can look at the Haar basis, where it starts with just the indicator function of the interval 0, 1. Then you have this Haar vector, and then you dilate it to the interval 0 to a half, and then translate that to a half to 1, and then keep going. And so this will be an unconditional Schauder basis for p strictly bigger than 1, and it's a conditional Schauder basis for p equals 1. Another nice example is the Fourier basis. And this will actually always be a conditional Schauder basis, except in the case that p equals 2, in which case it's a orthonormal basis. So things to point out is here, we start off with a positive function, and all of the other functions we have are mean 0. And so if you integrate them, you get 0, and so they're definitely not positive functions anymore. And for the Fourier basis, we have the same property. We start off with a positive function, and then all the others are mean 0. And so what we want to do now is think about what kind of coordinate systems you can build where all of the vectors are positive functions. And so one thing to point out is that these bases that we're going to construct are going to look absolutely nothing like anything you've seen before. So start off with some negative results on non-negative coordinate systems. So what kind of coordinate systems are impossible if you only use non-negative functions? And so the first result is that you can never have an unconditional Schauder basis for capital LP for any P if you only use non-negative functions. And Powell and Spaeth extended this to unconditional Schauder frames as well. And so if you want to build a frame for LP where all the vectors xj are positive, then it can't be unconditional. And Johnson and Sheckman extended these results so that if you have a sequence xj, which is a normalized unconditional basic sequence for its span using only non-negative functions, then it must be equivalent to the unit vector basis of little LP. And so essentially, if you have an unconditional basic sequence of positive functions, pretty much the only way to do that is to make them disjoint, and then they'll be equivalent to the unit vector basis little LP. Furthermore, if you have a subspace of capital LP with an unconditional Schauder frame, and the vectors are non-negative, then that subspace embeds into little LP. And so essentially the only subspaces of capital LP which can have unconditional coordinate systems are little LP, if your unconditional coordinate systems are made by positive vectors. So I wanted to give a sketch of the proof that capital LP does not have an unconditional Schauder basis of non-negative functions. And so suppose we have one. So suppose we have xj, which is a sequence of non-negative functions, and it's an unconditional Schauder basis for the whole space. Now we're going to look at the Rademacher functions. And so the Rademachers are, you can think about them as independent plus or minus one random variables. And so they just alternate between 1 and -1. Keep going. And I'm specifically looking at the case P bigger than 1 because the case P equals 1 is kind of obvious because L1 doesn't even have an unconditional Schauder basis. And so it definitely doesn't have an unconditional Schauder basis of non-negative functions. And so we can assume that P is between 1 and infinity. And now we know that the Rademachers are converging weakly to 0. And whenever you have a sequence which converges weakly to 0, you can find a subsequence which is a perturbation of a block sequence of our unconditional basis. And so by passing to a subsequence, we can find a block sequence yn and write it this way, so that yn is a perturbation of the Rademachers. And now because yn is a block sequence, we can look, and xj is unconditional, we can put the absolute values of on the coefficients. And as our sequence xj is non-negative, the absolute value of just the coefficients is the same thing as the absolute value of the coefficients times the vector. And so this is the key point where we use that the xj's are positive vectors, because then the absolute value of a coefficient times the vector is the same thing as the absolute value of the coefficient times the vector. And then now, this is then going to be bigger than yn, because the absolute value of yn is just the absolute value on the outside. And so by triangle inequality, this is bigger. And so now we're going to get a contradiction because yn is a perturbation of the Rademachers, and that's going to contradict that the zn converges to 0. And so I just want to kind of explain that. And so this Rademacher is essentially, this is our y vectors up to some small perturbation. And then the zn's are going to be above the absolute value. So this could be z1, this could be z2, and so on. And so we have our z vectors are above the absolute value of yn, and then you can see that Zn is not converging weakly to 0 now, because if you just integrate from the interval 0 to 1, you're going to get 1. And so Zn does not converge weakly to 0, but that's a contradiction because it is a block sequence of because it's an unconditional basic sequence. And so every unconditional basic sequence in LP converges weakly to 0. So that's our contradiction. So, so that was negative results. Let's talk about positive results on non-negative systems. And so we know that we can't get any unconditional structure using positive vectors. And so let's see what happens if we get rid of that condition of unconditionality. And we have that LP always has a conditional Schauder frame so that the vectors are non-negative. And also LP has a Markushevich basis where all the vectors are non-negative. And so if we get rid of unconditionality, we have these results. And Johnson and Sheckman proved that, furthermore, for the case p equals 1, L1 has a Schauder basis of non-negative functions. So these were the known results. And something that's kind of funny is the Powell and Spaeth paper was written first, but for some publishing funny thing, the years are different. Okay, so these were the known results. And so what we proved was that capital L2 has a Schauder basis of non-negative functions. And for the case that P doesn't equal 2, we can't prove that LP has a Schauder basis for the whole space of non-negative functions, but we did prove that it contains a basic sequence of non-negative functions so that the whole space embeds into the span of the basic sequence. So just to recall, Johnson and Sheckman proved that if you have an unconditional basic sequence, then it's equivalent to little LP. And so we have, for any P, you can find a conditional basic sequence so that the whole space embeds into the span. Okay, so what I want to talk about now is an idea for basically how to construct this construction of Johnson and Sheckman. And then from that, we're going to see how could that be extended to LP. Okay. So the first thing we're going to do is take the indicator function on the interval 0 to 1. It seems like a good place to start. And then now we want to build a basis for all of L1. And the way that you can guarantee that is by guaranteeing that the Haar basis for L1 is contained in the span of the ZNs. And so now what we want to do is create our next two vectors so that they contain the first Haar vector. I want to give myself a little bit more room. So Z2 is, actually, let's make it a little bit bigger. So let's say it's 2 on the interval 0 to 1/2. And then I'm going to put a piece outside of the interval 0 to 1. And so this will be Z2. And for Z3, I'm going to make it 2 on the interval 1/2 to 1, and then make it the same as Z2 out here. And so the idea is the har vector is contained in the span of Z2 and Z3, because if you just look at the difference, then divided by 2, you're going to get exactly the first har vector. But we want that this is basic, and so we need to make sure that we stay away from Z1. And so the point of this piece out here is that if you subtract these two vectors, you get the har basis, but if you add them together and try to get Z1, you get this extra piece out here as well. And so this is going to be far away from Z1 because this extra piece is contained in Z2 plus Z3. And so to do the same thing for the next har vector, if you want to make Z4, we put a big piece over here and then put another disjoint piece as well. And let's get rid of this. And so then Z5 is going to be big on the interval 1/4 to 1/2. Then it has the same extra piece as Z4. And so if you take Z4 minus Z5 over 2, this is going to be the next har vector. So I'll call that H2. But Z4 plus Z5 over 2, this is going to be far from everything else. Okay, so that's the idea, that you inductively build a basis by splitting up har vectors into two parts and adding on a disjoint piece. And it works out. Obviously, I haven't proved anything. So in their paper, they prove that this will actually build a basis. And so the first thing you might consider is, why does this only work in L1? So they're smart guys. They would have checked, why doesn't this work for other P? And so if you think about what's happening, Z1 is 1 here. If we did, so this is Z1. If we did Z2 plus Z3 over 2, it's the same on this first part, but we got this extra piece over here. And now if we add up the next level of har vectors and take, and so this would be Z4 plus Z5 plus Z6 plus Z7. They're going to have this extra piece over here, and so in L1, these extra pieces add up according to little L1. But if we let's go one more level, we do the same thing. And so we average the next har vector, so it'll be 15. So in L1, all of this pieces that we've added on add up like little L1. But if P is bigger than 1, all of these extra pieces are now converging weakly to 0. So if P is bigger than 1, the leftover parts goes weakly to 0. And so what you're going to have is a block sequence which converges weakly to the indicator function on 0 to 1. And so you can't have a block sequence converge weakly to something in the sequence. And so this can't be a basis for P bigger than 1. And so that's the idea about why it doesn't work for P bigger than 1. Okay, so we're gonna do something different to get the Schauder basis for L2. So we're gonna use this Johnson-Shechtman idea, but we're gonna have to do it in a more complicated way. And so the idea is, in order to build a basis for L2, what we'll do is, so this should be epsilon sub j. And so we're going to take some epsilon j, which is converging very quickly down to 0, and we'll consider some orthonormal basis for L2. And without loss of generality, we're going to make the first vector the indicator function 0, 1, and then the second vector the har vector, just for ease of understanding in the talk. And so I want to build a basis for L2 just with positive vectors. And so we'll start off with the indicator function of 0 to 1. And then now what we want to do is add on basis vectors so that we can reconstruct U1. And so the idea is that I want to make sure that I'm building a basis for L2. And the way that we'll do that is I'm going to add on a bunch of vectors which can reconstruct U1, and then I'll add on a bunch of vectors that can reconstruct U2, and so on. And so for the Johnson-Shechtman idea, they just added 2 vectors, Z1 and Z2. However, we're going to make a lot of vectors in order to reconstruct U1. And this number of vectors will determine how big that has to be later. And so we're going to make a whole bunch of vectors so that the orthogonal projection of our first vector onto the span is extremely small. And so we're going to add on a bunch of vectors that are almost orthogonal to Z0. And we're going to do that so that the distance between U1 and the span of the vectors of our new vectors is going to be really small. And so we're adding a bunch of vectors that are almost orthogonal to Z0, but so that U1 is extremely close to the span. And then in order to get U2, we do the same thing. We're going to add on a whole bunch of vectors. N2 is going to be huge, so that if you take any vector Z in our previous initial segment of the basis, then the orthogonal projection of it onto the span of our new vectors is going to be very small. And so that U2, if you project it onto the orthogonal complement of what we've already done, then it'll be very close to the span of our new vectors. And so if we looked at the Johnson-Shechtman construction, you can reconstruct, so the second har vector is actually orthogonal to all of the previous ZNs. In our construction, U2 isn't going to be orthogonal to Z1 through Zn. And so we project U2 onto the orthogonal complement of the basis vectors we've already created and make sure that this projection onto the orthogonal complement is close to the new vectors we create. And so this is the strategy for building a basis for L2. And I just wanted to point out is the reason why we can't use this to build a basis for LP for P not equal to 2 is this step 3 right here. So in step 3, we're doing an orthogonal projection, which doesn't exist in LP for P not equal to 2. And so this step 3 is what fails for P not equal to 2. Okay, so let's talk about how to do this step 2. And this is going to rely on a lemma in finite dimensional little L2. So the idea is we have some allowed error, epsilon greater than 0. Then we're going to pick a gigantic capital N depending on epsilon so that we can find a sequence in L2 of dimension 2n, direct sum L2 of dimension 2n, so that the sequence we create is 1 plus epsilon basic. And so that if we take the orthogonal projection of this constant 1 over root n in the first coordinate, the orthogonal projection of this vector onto the xj's has extremely small norm. So this vector with just all positive 1 over root n is pretty much almost orthogonal to our basic sequence. However, if we alternate signs, so -1, +1, -1, +1, then this vector is going to be extremely close to the span of these xn's. And so you can maybe see how this could help us, because in building a basic sequence, this would play the role of the constant vector indicator function interval 0 to 1. And we want that to be almost orthogonal to our basic sequence. And this is going to play the role of a Haar vector, and we want it to be close to the span of our basic sequence. So start off, here's how you choose capital N.
And someone's asking if xn is positive.
Yes, oh, that is key and positive. Yes. Yeah, so I don't see the chat, so if maybe I can
click on chat on the bottom of your screen.
Yeah. Yes. Okay, yeah, now I see the chat. Yes, exactly. I can't believe I forgot that, because that's like the #1 key point, is that this xn is positive.
Let's see. Dan, I want to ask a question at this point. Maybe it's obvious that this implies then the sequence you construct is has big unconditional constant.
Yes.
Why is that? That should be obvious. Why is it obvious?
It's obvious in the construction. It's maybe not obvious in the statement of the lemma.
Oh, okay, okay.
Because the way that we're going to do this is in the construction, the closest vector, if I do the orthogonal projection onto this span, the closest vector is going to be essentially an average of these. And then this vector is going to be extremely close to plus or minus ones, that average.
Oh, okay, yeah, thanks.
Yeah. So in the statement of the lemma, it's not obvious, but in the construction, it is. Yeah. Okay, so we need to choose capital N extremely big so that there's a sequence of AJs such that this is true. And essentially the way that you can do this is by picking AJ is some constant over J plus 1 log J plus 1. So the idea is that if you can pick a small constant C so that this series, so this series is not summable, but if you look at this series here, this will be convergent, and so by picking a small c, you can guarantee that this is possible. And just for notational convenience, we are going to call the sum of the coefficients capital A. And now we're going to define the xn's on the next page. And this is what they look like. And just to point out that this is based on a modification of construction in Albiot-Calton on how to construct a conditional basis for little L2. And so we took their construction and modified it in order to do this. So let's think about what's going on here. If we just look at, let's just look at the vector x1 to start. So it's 1 in the first coordinate, and then in all of the even coordinates, it's this AJ sequence. And then on the left side, I get rid of the 1 and then multiply the AJ sequence by epsilon. So essentially, this part over here, if I'm just looking at this vector x1, is like a 1 here with a teeny bit added on. And the part added on the right is much bigger than the part on the left. And then for the even x2, it's just 1 in the second coordinate. And over here, it's epsilon in the first coordinate. And what's going to happen is I have odd vectors and even vectors. The odd vectors are just going to be cyclical rotations of x1. And so x3 is I shift the 1 over, I shift all of the AJ sequence over. And same thing on the left, it just gets shifted around. And so x3 is just the shift of x1 by 2 to the right. And likewise, x4 is going to be the shift of x2 by 2 to the right. And so what we have is this nice kind of cyclical matrix. So let's think about why this will give us our lemma. So first, this is clearly positive because all the AJs are positive. The 1 plus epsilon basic, that requires a proof, and it uses that the AJs have this property. The proof is very similar to the proof in Albiot-Calton. And then now we want to check that the orthogonal projection of this vector onto the span is going to be extremely small. So I'm not going to prove that, but I'm going to try to give an idea of what happens. So if I want to create a vector that is on this left side, just constant 1 over root n, the way that I would do that is all of the, I would take an average of these. And so all of the odd vectors, I would divide by epsilon times a root n. And so I'm going to add up all the odd vectors, divide by epsilon a root n, and that will result in these coordinates all being 1 over root n. Then if I take the even vectors, there's no a here. And so if I just divide by epsilon root n for the even vectors, I'm going to get constantly 1 over root n in this coordinate. And so that's going to be exactly this right here. The problem, though, is what happens on the right. And so the part on the right has much bigger norm than the part on the left, because the part on the left is multiplied by epsilon, which is tiny. And so if I add up the part on the right, in the odd coordinates, I have 1 over epsilon a root n. Then in the even coordinates, I have 2 over epsilon root n. And so what happens is, on the right, I have this 1 over epsilon in these coordinates, and epsilon is extremely tiny. And so this norm on the right is going to be huge. So the norm on the left, this will be, because there's 2 capital N coordinates, this will be have norm root 2. On the right, the norm's going to be about 1 over epsilon, which is huge. And so essentially, if I want to find the closest vector, if I take the orthogonal projection of this vector onto this span, what it's going to look like is a scalar multiple of, it'll be very close to a scalar multiple of this vector. And in order for this right side to be small, it's going to be a scalar multiple of this vector times something extremely small. And so the orthogonal projection of this vector onto the xj's is going to be extremely small, because the part on the right, when we use positive signs, is going to be much bigger than the part on the left. But if we alternate signs, and so if we have -1, +1, -1, and so on, what happens is the even terms cancel. So if we use only positive terms, the even terms add up and give us a 2. If we alternate signs, the even terms all cancel. And so we're just left with these odd parts. And this is the key part where A comes up. And so we have capital A is very big. So in particular, epsilon times, so 1 over epsilon times A is smaller than epsilon. And so this part here, the norm of the right is approximately epsilon, and the norm on the left is root 2. And so what we have is that if we just use positive signs, the left has norm root 2 and the right has 1 over epsilon. If we alternate signs, the left has norm root 2 and the right has norm epsilon. And so this is the idea of how we're able to construct these xj's so that this vector is very far from it, but this vector is very close. Okay, so that's our key lemma. And so now I'll talk about the idea for how we use that to construct the positive Schauder basis for capital L2. And so if we think about the Johnson-Shechtman construction for L1, in each step, they took a Haar vector, split it into a positive part and a negative part, and then they added on a positive part disjoint to both of these. And so they split their vector into 2 pieces and added on an extra piece. And then we saw that that's not going to work for p other than any p bigger than 1. And so what we do is we still split our vector into a positive part and a negative part. And then for each of these, the positive part and the negative part, we further split into an extremely large number of parts. And so this capital N is going to be what's given from our lemma. And so we split into a huge number of parts. And then instead of just appending a single positive vector to both, we append our conditional basic sequence that we constructed to both. So let's look at basically how will that look. So if we want to construct z1 through zn in order to reconstruct the Haar vector, give ourselves a bunch of room. And so let's say this is the interval 0 to 1. So we cut this in a bunch of teeny subintervals, so capital N subintervals. And then on the right, we're going to make 2n intervals of length 1. So if we want to look at what is our first vector z1 going to look like, it'll be on this first interval 0 to 1/2. It's going to look like this, where this first part is epsilon a1 root capital N. The second height is epsilon a2 root capital N, and so on. And then for the disjoint piece, this will be 1, then a1, a2, a3, and so on. And so this is a graph of z1. So it's essentially building in our lemma. It's going to look just like the vector x1 in the lemma. Then if we want to make z2, it'll be, so z2 is 1 here, and it's going to be epsilon root n here. So this is z2. And then for all the odd vectors, we're just going to cyclically shift z1 in order to make z3. And so I'll put z3, I'm going to draw it on top. So z3 is going to look like this. And so in blue, we have z3, and then it's going to be shifted here. And then for z4, we just shift z2. So it will look like this. And so we keep building our sequence like this. And so all our odd vectors are shifts of cyclical shifts of Z1. All our even vectors are cyclical shifts of Z2. And if we look at, so it'll be, what will, in order to construct the Har vector, we'll do 1 over epsilon A root n times the odd minus the sum 1 over epsilon root n times the even. Then when we do that, what we're going to end up with is the first Har vector with, and then this stuff here is going to be really, really small. And so we're able to approximately reconstruct the first Har vector in such a way that all the vectors that we built are almost orthogonal to the indicator function from 0 to 1. So that is the idea for the construction. I have a couple more things to talk about. So the way that I got interested in this project was because Alex Powell was working on coordinate systems of positive functions, and I had done some work on coordinate systems of translations of a single function, and we thought it'd be interesting to see what kind of connections and ideas we might be able to share and across the two ideas. So let's talk about coordinate systems of translations of a single function. And so for any p and any lambda, t lambda, we're going to call the right shift operator. And so it takes a function f, and then it shifts it to the right by lambda. And so instead of thinking about what kind of coordinate systems of positive functions can you make, we can think about what kind of coordinate systems of translations of a single function you can make. And we'll first consider negative results. So first off, if you only translate by integers, then the translations of a single function do not have dense span in LP. So for any function that you take, if you only translate by integers, its span will not be dense in LP. Furthermore, for any p in any translation, you cannot get an unconditional Schauder basis for the whole space. And different p's were done in different papers. So Olsen and Zalek proved it for p equals 2. Odell, Sari, Schumprecht, and Zhang proved it for p less than or equal to 4. And then we proved it for p bigger than 4. And also, if you want to consider frames, for the case L2, the translations of a single function will never be a Hilbert space frame for L2, no matter what you translate by. And here are some positive results. If p is bigger than 2, then you can always find a function who has dense span in capital LP if you translate by integers. And so here, if p is less than or equal to 2, translation by integers will never have dense span. And this follows from a pretty simple Fourier transform argument. But for p bigger than 2, you can get dense span. And the reason for that is that the Fourier transform on LP for p bigger than 2 gives you a distribution as opposed to an element of LP. And this is, I think, the most interesting, striking result. So we know that you can't translate by integers to have dense span. However, if you translate by teeny perturbations of integers, you can get dense span in L2, which is shocking. So you can't translate by integers and have dense span, but if you translate by almost integers, you can. And we proved that if p is bigger than 2, then there is a function and a sequence of functionals such that its translates by natural numbers is an unconditional Schauder frame for capital LP. So this is one of the key differences between positive functions, because we know that you can never get any kind of unconditional structure for positive functions, but for p bigger than 2, you actually can get an unconditional Schauder frame. So one of the things we looked at was what happens if we combine things. And so now instead of just looking at a positive coordinate system or a coordinate system of translations of a single function, what about coordinate systems of translations of a single positive function? And we proved that for any f in LP, for any p, you can find a sequence of functionals and a sequence of constants to translate by, so that we get a Schauder frame of translations of a single positive function. And this follows from a general theorem that we proved. And the proof of this is inspired by Pelczynski's proof that every space with the bounded approximation property is the projection, or embeds as a complemented subspace of a Banach space with a basis. And so we proved that if you take any dense subset of X, or any subset whose span is dense in X, then you can construct a Schauder frame whose vectors are elements of that set. And here's a bunch of, in what my opinion is very difficult open questions. And so we constructed a basis for L2. Johnson and Sheckman have it for L1. But for any other P, does LP have a Schauder basis of positive vectors? You can also extend this to more general Banach lattices. And so if you look at the continuous functions on the interval 0, 1, the classical, I guess what do you call it, the triangle basis for that, is a Schauder basis of non-negative functions. So you could ask which separable Banach lattices have a Schauder basis of positive vectors, and you could also ask which separable Banach lattices have a Markovitch basis of positive vectors. So this one might be more approachable because capital LP always has a Markovitch basis of positive vectors. You could also ask, given any Banach lattice, does it contain a basic sequence of positive vectors so that the whole space embeds into the span of your basic sequence? And this is a big question. Can you ever get a Schauder basis of translations of a single function? So the difficulty for this is the basis that we've seen for positive vectors are for L1 and for L2. However, the coordinate systems, the nice coordinate systems for LP are for P strictly bigger than 2. And so we don't have an overlap on the P's where we can build nice bases or nice coordinate systems. So thanks a lot for listening and for having me.
Thank you so much, Dan. That was such a beautiful talk. We can, yeah, so this is the virtual thing. So we can open up questions. There are a couple in the chat, or if someone wants to voice the question, let's start with those maybe.
Start with the chat questions?
Let's start with voice maybe. That will be, or maybe those people can just voice those. It's hard to read from here.
So my question is, can those constructions be done on LP, on L1 of 0, 1 and L2 of 0, 1?
Yes, as Banach lattices, they are isomorphic. And so actually the construction that we do works for L2 of any measure. And same for Johnson and Sheckman's construction for L1. It works for L1 of any measure. Because for like little L1 and little L2, it's obvious that there's a positive basis. And so any LP of any measure can be characterized in terms of little LP and capital LP of R. And so it will work in those spaces as well.
Thank you.
Is there any philosophical sort of explanation of overlap between the translation problem and the positive problem, or is it just a coincidence that some of the results are?
It's I had worked on one and Alex had worked on one, and we were talking with each other.
Okay.
So it's a overlap of so it's basically we both came from different.
But in terms of positive and negative results, there are some overlaps also.
Yes, there's a lot of overlap for the positive and negative results, and so that's part of what I think's interesting is that there's not complete overlap, but some of there is definitely.
Okay. Okay, Vladimir has a question. If you want to say it, you can go ahead, Vladimir Kada. What property? Yeah, go ahead. Okay.
The question is that you're constructing a basis whose elements lie in the positive cone of L2 of function. So the question is, what properties of positive cone are essential here? The very strong question is to characterize those cones in Hilbert space which contain a base.
Yes. So the go here. So the main thing is so step 1 and 2. This will work for any LP. So we can construct a positive basic sequence which starts with the indicator function of 0, 1, and then everything else will be far away from that, and we can reconstruct the Haar vector. The difficulty is that when building a basis for the entire space, you need to make sure that the basic sequence that you're building is nicely complemented in it.
Oh, the emphasis of my question is forget about any other spaces outside of Hilbert space.
Oh, okay.
What kind of properties you should demand from a cone to have a basis which lies in this cone?
So if you're in a Hilbert space, any Hilbert space this will work in.
I think the question is, Dan, the cone, for example, just take another cone, like just take one coordinate negative, everything else positive. So do you use anything special to that cone? That's the question.
That's a really interesting question. Okay, I understand what you're asking now. That's very interesting. I had not thought about that. So I can't tell you but that's something I'll think about.
But it looks natural.
Yeah, it's a very natural question.
Short question.
Okay,
Unconditional basis is the same that extension of vector converge by norm?
Say that again?
Unconditional basis is the same request that extension of vector relative to this basis converges by norm to this vector.
Yes.
Thank you.
Okay, thank you. Another question on the chat, you see it probably?
Yeah, so capital N, so the way that we pick it is so that this series condition holds, and so it'll be, so essentially you need to pick capital N big enough so that if you add up 1 over j plus 1, ln of j plus 1, then it's bigger than this, but smaller than this. I think it's going to be exponentially large. So it's going to, I would expect that you could do some calculus to figure it out, but I haven't done that.
Okay, thank you. Any others?
Yeah, so Daniel, first of all, thank you for a very nice talk. Second, can you maybe scroll down a couple of slides? Sorry, in the other direction. So there was this slide about the existence of a frame of translates.
Oh, that's yeah.
Yeah, towards the very end. Yeah, the last one. So here, can you make also the frame functionals to be translates, or is it impossible? The G's.
So the G's are actually, the way that we pick the G's, these will be actually har vectors, and they will be, so I put 2 citations here. We proved that such a frame exists, and then they proved that you can do it with picking the GJs normalized, or semi-normalized. The way that we did it is to guarantee that you have a Schauder frame for LP. We proved that you can reconstruct each har vector, and the GJs are going to be the normalizing functionals of the har vector, repeated a whole bunch of times and then scaled down very far. So the way that we did it, the GJs are not at all translations of a single function. I kind of feel that you can either impose structure on the vectors or impose structure on the functionals. I don't know if it's possible to get the GJs also translations of a single function. I think that would be extremely difficult.
Thank you.
Hey, thank you. Any others? All right, probably not. Well, Dan, thank you so much. That was such a beautiful talk, and thanks for doing this. Thanks everybody for joining. Okay, Jill has something. Go ahead, Jill.
Sorry to interrupt, Benjamin.
Go ahead.
There is, first of all, thank you for this nice lecture, of course. Then there is a nice work by Nigel Calton and Lemerdy in the late 90s, where they answered a question of Peller about power-bounded operators on L2, whether they were similar to operators so that the supremum of the norms of T to the n is close to 1. So they answered this negatively by using multipliers on the conditional basis of L2, of the Babenko conditional basis of L2. So that's a paper of 99, I believe. Okay. And now you have conditional basis of a different kind. I wonder whether you can confront your results with their approach and maybe finding, I'm not sure, of course, positive operators with this type of behavior. I don't know if you are familiar with this work.
I'm not. That's an interesting idea. I will look that up.
Okay, so Calton and Lemerdy again are the authors of this nice work.
Great, thank you.
Okay, thank you, Jill. Okay, I guess that's all. Thank you again, Dan. So you can turn off the share screen, and people. So we can do the social hour now. So I'm just gonna stop recording. So what we do is we just